So we had this, so what we were doing? Last time we were talking about recurrent neural networks, be it RNNs, be it LSTMs, GRUs, whatever. So consider these units as only those units for the time being. Okay. Now in RNNs, these units have a feedback. So basically the output of this will go here, the output of this will go here, and so on. And we had listed it as one of the problems for RNNs because that slows down the training, because you can't use GPUs effectively. That is inherently sequential. What we are trying to propose here in this case is we want to get rid of those recurrences. So we don't want them, and can we still keep on doing things? So what was the reason why did we have RNNs? We wanted to encode this sequential nature of language, first word, second word, and they are doing it one after the other. But in the end, what do you do in deep learning? In the end, you try to learn representations. Okay. So in the end, you try to learn a very good representation of your input. So what we are saying, remove those hidden layer, this feedback mechanism that we had, these arrows from H1 to H2, and all we are saying is in the next layer. So if I rotate this 90 degrees clockwise, you will see something similar that we had seen a neural network in deep learning, the earlier course, right? Because there you had x1, x2, x3 all the way until xn, that was my input layer. Then you had the first hidden layer, then the second hidden layer, and then keep on doing whatever you wanted to do. If I rotate, it is just the same. In this case, what is happening? In this case, my input is not just one scalar or categorical vector or a real number. It's not like we had in the case of normal feed forward neural networks. Here your input itself is a 300 dimensional vector, which is the word embedding. Okay, and we are specifically talking about language, we are specifically talking about words here. So all these are words, the input. You input word embeddings learned through word2vec, GLOVE, fast text, whatever, and then you want to learn good representation so that towards the end you will be able to do the task that you want to do. So what are H1s? So you take this as input, word embedding, and you convert this into, so WH1, what will be these guys? See, again coming back to this, what we were doing. So you compute basically H, okay, at you compute the representations at each layer. How are we computing self attention here? Instead of doing S dot T, S transpose dot H, we don't have any S now. So what we are saying, you just take the same operation with respect to all these guys here. So when you are talking about the self attention here, what is this vector? H1 dot, so H1 transpose H dot plus, not yet plus, H2 transpose, no wait, this is H1 transpose H1, this is H1 transpose H2, this is, so this third arrow is H1 transpose H3 and so on. So how many do you have here? Tx, that is just for this one. So you have a vector of size 1 cross Tx just for this one. Now what does, so these are called attention scores, and then we compute softmax of that gives you how much weightage to give H1, H2, H3 while computing the representation for this first element. So whatever, let's say if this is H1 prime, so how much emphasis should be given on H1, how much emphasis should be given on H2 and so on if I want to compute the representation here. This is what we had done yesterday. Okay. And then we also had some discussion post class that will eventually we will have here as well. Okay. Now how do you compute this H2 prime? H2 transpose dot H1, then H2 transpose dot H2, H2 transpose dot H3 and so on. So you can compute. So you will get, so what will be the size of attention score here? Same, 1 cross Tx. Okay. And you can keep on computing. So we had said that you will get a matrix of size what? Of size. So this is, so 1 cross Tx for Tx many, so this is Tx cross Tx. Okay. And you keep on doing this until you want. So if you want to compute the output of self attention here, what will you do? Same thing. H1 prime transpose dot H1 prime transpose dot H2 prime and so on. So I think this part is clear. Okay. So this is what self attention is. I mean, this is what attention is in general if you want to do it on the same sentence. Okay. So the question that we are asking now is, do we need this recurrence at all? Okay. Do we need this recurrence at all? What is your take on this? See, in RNNs we had this, if you are going from t minus 1 to t, so there was, you know, we were passing this a or h or whatever you were calling it. 3 problems suffered by RNNs are vanishing, exploding, inherently sequential, and too much emphasis on this last one vector. Okay. So we want to, so we have seen that, I mean, even though I have not done it formally here, but attention, it looks like that it improves vanishing and exploding gradient. So we have not discussed because I have not done the backpropagation of RNNs in detail here. Second, what was the second one? The burden on just one input, right? That's no longer there. Last thing, can we get rid of this inherent sequence? Right? So it turns out you can. That is what transformers do, right? And the title of the paper was Attention is all you need. That means you don't really need recurrence as such. Okay? And in fact, you need much more than just attention. But this title actually means you don't need recurrence, attention mechanisms are sufficient. Okay. Alright, so now then let us start today's class. Okay. So now let us talk about self-attention. What is cross-attention? What is cross-attention? Guys, dekho, I am going super slow here because these are the building blocks. If we don't understand each one properly, later, I mean, there are problems. Yes. What is cross-attention? If you have encoder and decoder and you use representations in both to compute attention, that is your cross attention. Self attention is There is no encoder decoder, just one architecture, and you are computing attentions among themselves. Okay. So, if you remember here, let me go back. This is 2. Right, this one here. In this case, what was the query? I mean, we were querying corresponding to which vector? See, this nomenclature throughout deep learning has been very confusing. Like if you go to CNNs, there is a kind of padding called same and valid. They just don't give you any information, and why should one keep such names? But you know, one person was writing a paper, they had much better job than, you know, looking for good names, and that paper became super famous. So now whatever nomenclature they had used remains in the literature. The same thing here. Now tell me, what is this query? But they do try to connect it to databases. I won't do that. I find that more confusing. We are but we will still use that same name. So which vector, if I want to assign, if I want to call query vector, which one is the best candidate for that? Why? So this candidate is the best one because before giving output y hat, it is trying to go and ask every edge, what is your contribution? Roughly, that is what is happening. Okay. So this is your query vector. Okay. Now these are, now you need to write down, these are called values, and something are called keys. Okay. So 3 vectors we will be talking about. Query vector is the easiest of them to understand. Now, how were we computing attention in this case? S1 transpose dot H1. Okay. So S1 transpose dot H1, that gives us, so let me, this figure is now clear, let me go back to what we were doing. Okay, so initially in okay. Now what we were calling this, what were the other thing? H. So what was HT? Values. Okay. These were the hidden states, I mean these were the values from encoder. Okay. Now what transformer paper does is that it introduces 3 things. So query, key and value. Query is the most intuitive thing. Okay. Now what does value do? So remember, we were doing what we were doing in attention when we were computing for whichever, be it self attention there or be it cross attention. We were computing dot product of 2 vectors, right? Dot product of not 2 vectors, basically we were computing dot product of tx vectors. with ST, with the query single. So single query vector and multiple H vectors that we are calling values. You take their dot products and then what do? Take softmax of the outcoming, the resultant vector, and then make a linear combination of HT. Everybody understands here linear combination? Linear combination means scalar times vector 1 plus scalar times vector 2 plus some another scalar times vector 3 and so on. So this is called linear combination. So how are you computing attention score? Dot product of these two guys. How are you computing your final AT? Linear combination of these guys coming from, so linear combination of these guys, in every linear combination two things will be involved. One is vector, another thing is the scalar. So vector is coming from here. Where is the scalar coming from? Also from here. This guy has contribution in computing scalar as well. So the transformer paper says, I don't want to do this. Okay. Transformer paper says query remains what it was earlier, so there is no dispute over there, but I am not going to take dot product with the same vector and then later use it as a, later compute those same dot products to compute linear combination of these guys. Does it make sense what I am saying? Okay. So transformer paper says I need three things. So there will be a query vector, let's, for the time being, I don't know, later I will change. So why should I do that? So as transformer paper says, my query vector is, let's say Qi. Okay. So key vector is Ki. I need small k, and value will be Vi. Okay. So I have given enough hint for you to figure out what will transformer people do now. So they say, and let me make sure what I am saying is right. It turns out, yes. You decide, you tell me. Other suggestions here? Okay. Other things? वो सब कहाँ है? प्रियांश और ये सब ये रिकॉर्ड करना कभी कभी बैकफायर भी करता है ना. So I'll randomly choose a day and assign all 5 marks to that class. And करते रहना मेरी शिकायत. Yes. Okay, coming back to what we were doing. So what should be query? Query is a vector. Okay. What should be key? I thought I have given enough hint. Query is a vector. Now you want another set of vectors corresponding to your inputs with which you want to take dot products, and then you want a third vector whose linear combinations you will use. Okay. So you take dot product of these two guys. So transformer paper comes and says, see, until now what you were doing, taking dot product of these two guys, whatever vector comes, take softmax of that and take weightage of that again to compute weightage of these guys in your final attention output, in your final AT. Don't do this. Transformer paper says use a third vector, use a different vector called key. You will take dot product of these guys. Now Output of these two have nothing to do with this. Now, whatever attention scores you get from this, and after that you do softmax, now linear combination should be taken of these guys according to the computations you have got from these guys. And I'll spend a lot of time here, so don't worry. So now how do I compute the these values, I mean the attention scores? You can help me, I mean I'm pretty sure you know everything. So let me, so now I am not going to draw that thing again. So you have Tx units at the bottom. So how do I compute the first attention now? So Qi is my query, and so I am doing it for the first unit so that I don't want to use generic labels right now. Let me try to be as specific as I can. So how will I compute? So what will I do is Q1 transpose K1. This will what I do at, I mean dot of course. I hope it does not hang. And then what will happen at the second one? Okay, so that is the first. Now what will happen next? Q1 transpose dot K2. Next. So last will be Q1 transpose dot K Tx. What is Tx? So number of words in my current sentence that I am talking about, okay? And it can be a document, I mean I am calling it a sentence, but it can be a sentence, a paragraph, a document, it may not be even a complete sentence, right? So nobody stops you from, so there is no limit on what this Tx can be. It has to be just a sequence of words that make sense, okay? It cannot be just a random sequence, at least not for all the purposes. Now you have this one. So what is the size of this vector? So this gives me, what will be this value? E11, E12 all the way until E1tk Tx. Okay, and this vector is of size and this was computed just for, okay. Now what do I do next? So what will softmax give me? Whatever it does. Okay, so in paper, I mean at least in Stanford slides, they are calling E1, E2 after taking softmax, okay. So what do I do? So take softmax इसको हाँ ठीक है. Okay, so take softmax, and now what will you do? So E11 times, चला स्टूपिडिटी की भी हद है. एक सेकेंड, ये सब मेरे को जो है एडिट करना पड़ेगा, बट दिस E was right. Okay, so this E was right. After taking softmax, what we have is alpha 11, alpha 12, alpha 1 Tx. Okay, so E's are our, नाम क्या था इनका, इस वेक्टर का, attention scores after taking softmax, right? We don't give it any name as attention distribution, right? And then now what do we do? So now this guy gets multiplied with V1. V1 belongs to whom? V1 belongs to whom? First unit. Q1 belongs to whom? First unit. K1 belongs to whom? First unit. So every unit will have three different vectors called query, key and values. Queries and keys you will compute to get attention distribution. So until now, until here, so let me write it explicitly. Until here there is no contribution of VIs. Okay. So until now there is no contribution of VIs. Now we use VI to compute the final output. Okay. So alpha 11 V1 plus alpha 12 alpha 12 V2 alpha 1 Tx V Tx. You guys have to tell me. See, earlier you were doing first element times H1, then second element times H2. So now that H is being replaced by V. Right? Now, in theory, in principle, is there a way for this mechanism to fall back to what we were doing previously, in which we had only two vectors called S or called Q and H? Okay, so let me ask it this way. When we were doing cross attention, how many distinct vectors we had? S and H, right? And we were doing operations using only those two vectors. When we were talking about self attention, what is it that we were doing? So there was just one vector H. Take that vector to compute this dot product by dot producting with itself. Then take a linear combination of that same vector itself. Okay. So there we were overloading this H with three functionalities. Transformer paper comes and says, see, don't do this. What you should do is, you are the kind of operations you are doing, you kind of require three separate vectors. Now, is there a way for system to fall back to original one? I think this question you are not getting right now. So I'll drop it right now. My question is, okay, let me change the question. How do I get Qi, Ki, Vi? Okay. How do you get QIs or HIs? I mean, or what? KIs and VIs. So let me go back here again. I had left some space here. Sometimes, yes. So query Qi, you compute it as some Q times Xi. Okay, they call it Q or they call it something. Yes. Okay, this is K times Xi, and this is V times Xi. What is QKV? See, that's a good question. What is Xi? What can be input stream? So Xi is your input, which is the word. But how do you input word? Word embeddings. So Xi is the word embedding of this word Xi. Okay. Now if this is word embedding, what Q must be? What must be Q? Scalar, vector, matrix. I mean, of course, these two are matrix too, but what are the dimensions of Qi? Hmm? Your choice. Okay. So it is up to you. What dimensions do you? I mean, see, Xi is up to whom? That dimension 300 that we have been talking about all along, that depends on you. Okay. So these are mostly parameter. I mean, these are mostly hyperparameters. You want Xi to be 300. Once you fix 300, your other learnable parameters will get fixed. So those things which fix your learnable parameters, those parameters are called hyperparameters. Okay. So now, so let's say again we stick to our same thing. So if Xi is, what was Xi? 300 cross 1 and let's say for whatever reasons I want this guy to be 64 cross 1. What should Q be? 64 cross 300. So 64 cross 300. What should be the dimensions of Ki? It must be 64 cross 1 because you are taking dot product. So this guy must be 64 cross 1 and this guy is already 300 cross 1. This guy must be 64 cross 300. This one? So I have not revealed the whole thing, we will come to it, but for the time being, if this were not 64, some other number. So if you don't like 64, keep that number, okay. And I am not trying to use variables here, I could have done that, I could use variable, but fixing numbers actually help us visualize better. Now what about Vi? As such, there is no constraint here. There is no constraint that is coming from these two that fixes this, okay. But we want, for whatever reasons, that this guy should also be, so that makes it, so 64 cross 300. Yes. So these dimensions are clear now. So now we go back to what we were doing. When you are taking this dot product, that will give you a scalar. So once it gives you a scalar, you get E1. You take softmax, you get alpha 1. Now so alpha 1 1 alpha 1, these are scalars. Here you need vectors. So this, what is this final thing, guys? This is your, what we were calling until A. In these set of slides, they are calling it O. By the time this course ends, I hope you will be able to reconcile all this notation that we are using. Shall we call this A? आगे जाके देखेंगे, देखें कोई दिक्कत होगी तो. So we have been familiar with this A. Let us use AI. Okay. So what is it that we did? I mean, I have just covered one slide of these 70 slides. So what is this AI? What is happening overall? We want to do, we wanted to do this computation. We were calling this self-attention, right? But as they call in transformer paper, this is not self-attention. What according to transformer paper it is, you need to have these three vectors called query, key and values. You take dot product of query and key and then take linear combination of V. And this also solves this problem that you were asking, how are we going from here to here? What is H1? Right? So now in this case, what is Q1? It is a different vector. But what is the common source for all these three, Q, K and V? Your input word embedding. So three of them are coming from the same source. So for every unit here, you are computing three vectors, Q, K and V. K and Q you take dot product. So Q is your query, K is your key and values you take for final output. Okay? Transformer paper says attention is all you need. So there are no RNNs. They get rid of recurrence, but they still talk in terms of encoder and decoder. So next week we will talk about transformer architecture only, but we have already actually started. How many of you find we have done today's class just too slowly? है ही नहीं जनता क्लास क्लास में तो भूलेगा क्या करूं. But okay, now tell me one thing. If I want to fall back to what we were doing in encoder decoder, right? How will I fall back from here? At least in principle. Whether it will happen in practice or not, I don't know. So in my transformer architecture, right? In my encoder decoder architecture, the values were Q was S, K and V, both were identical, and that was H. Okay. Now if I want this architecture to fall back to this, how do you think it can do that? No, so what I want, okay, so let me tell you. You want Vi to be identically equal to Ki. So you want these two parameter matrices to be the same. So all these three are parameter matrices. Okay. Now if the network so believes that actually we are doing it wrong by using 3 vectors, actually there should have been only 2 vectors which will give us optimal results, what should network be able to do, at least in principle, if not in practice? At least in principle it should be able to learn K equal to V, because we are synthetically assigning it 2 different vectors. Network says no, I don't need 2 vectors, just one is sufficient for me, and for whatever reasons that is optimal too. In that case, network should be able to learn K equal to V. So it may or may not happen in practice, but at least in theory there is a way to fall back to the architecture in which you were using just 2 vectors and doing all this computation. Now how to fall back to that architecture in which we were using just 1 vector for all the 3 computations? Same argument, network should be able to learn Q equal to K equal to V. Okay. Now one more thing that we are doing. These parameter matrices were not there before. So if network also thinks that these things need not be parameterized, what network should be able to do? It should be able to learn Q equal to K equal to V equal to identity matrix. Now this is the way deep learning works today. It is too much to ask for, but at least in theory there is a way to fall back to any of the architectures that we have talked about before. This gives you the generalization of everything that we have done until now. Questions here? So QKV is done. We have talked about what is the output. So this is the right point to stop today. But I'll leave you with a question. What will be the question? You are asking something? No. So what will be the question? What are the problems with what we have done? So what are the problems in the sense? So we have solved this problem of, no, we have solved or not solved, but we have fixed these 3 vectors, we have fixed the way of computing attention, we have fixed the way of computing final output. This guy is still missing one thing, which is the recurrence. Anywhere in whatever we have done until now, do you capture this fact that this thing must have, this word comes before this? So the quick brown fox jumps over the lazy dog. The quick brown fox. Anywhere are we capturing this sequence? We are not capturing any sequence. RNN was doing it, right? So we have to bring this notion of sequence back without bringing RNNs back. Okay, and this is what positional encodings do. This we'll do in the next class. Chalo, done for today.